Okay, so welcome back, everybody. We're going to have Jim Kinnison speaking now. Jim is currently the Parker Solar Probe mission systems engineer, and his influence on this has been fantastic because of Parker's requirement to keep the payload mass down and the discipline that it takes to craft a meaningful science mission while not letting things like the mass of your payload run away from you, which increases the challenge, including the challenge of the cost. And so with that, I'm going to turn it over to Jim. Thank you very much, Jim, for preparing this for everybody today.
Thanks. Thanks, Michael, for that. I'm going to go ahead and share my screen, and we'll see how we can do this then. All right. All right, so if I could just get a confirmation that I have...
Yep, looks good.
Okay. So I'm going to present some material today talking about the concept that we produced, and you'll note that my title here is Concept Study System Engineer. And what that really means is I've got a really good group of people who've thought long and hard about this, and so I get to present all of this, but really they're the ones who've done the work. So I just wanted to say thanks to everybody on the engineering team, and I appreciate what you've done. I'll try to highlight out as we go along who those people are. You'll hear from some of them this week, and so I think it's going to be a very interesting set of discussions, especially as we go forward into the week. So really what we start with Interstellar Probe is, what are the big questions? When we come into developing a concept like this, the first thing we got to try to figure out is where are we going and how are we going to get there? What are we going to try to do when we get there? And so initially, even before I came on the project, there were folks who were working on launch system and the effective potential stages. There were trajectory options that were being developed, and also possibilities for science and definition of what science might look like on a mission like this. And also even some initial thinking on the constraints on a system that would accomplish this solar Oberth maneuver that we'll talk about a little later. So that was the first big question that needs to get answered. The second is, how do we control the spacecraft? Given the science that we're trying to do, what does the overall architecture of the system look like? How are we gonna operate it? And it's come down really to one of three possibilities, depending largely on the payload that we fly. A spinning system, a 3-axis system, or some hybrid that's a 3-axis that allows for spinning. And we have some heritage for all of these. I would particularly point to New Horizons, which is using that hybrid system very successfully. And so a lot of what we're doing is modeling what especially New Horizons has done in terms of the concept of operations and control and all those kinds of things. As part of control, we got to worry about pointing requirements and the control system associated with that. You'll see that for this mission is going to be dominated by the very large high gain antenna that we have to fly, really in every scenarios that we can come up with. So one of the things that we are doing, and we'll talk about this later, is looking at ways that we can decrease the size of that dish by going to Ka band, maybe using optical systems that would allow us to decrease the size of the dish, but then also add complexity in terms of additional pointing requirements and additional mechanisms that might be required for the system. The third question that we got to answer is, how much data can we downlink? This will always be a data downlink driven mission, given how far away from the Earth we're going and the capabilities that we have there and the limitations there. So there are a number of telecommunications trades that we've worked. I will give you a flavor of those today, and then we'll depend on Dave and Reza to clue us in on the rest of those trades and the details of those trades as we go on. One of the things that we have talked about a lot is onboard processing of science data, for instance, and how we can incorporate a large number of ideas there to allow us to get even more science out of the downlink that we have, right? And then finally, as Ralph has alluded to, and also Michael, how do we make the system last as long as needed? And here, one of the bigger concerns that I have is, what does that mean for mechanisms and electronics reliability? We have looked at missions that have lasted a long time and look like there's indications that if things get into space and we don't see a failure early on, that things tend to last very long in space. The question is whether we can count on that or not, and whether we can prove it sufficiently. We also need to fold into that fault management and autonomy. A system like this, given the round-trip light times, will be a very autonomous system, and so we have experience with that as well with Parker Solar Probe. So we're definitely taking advantage of that and thinking even now about what does autonomy mean, what does fault management mean, and how do we make a system that can really keep itself safe while we have the long light times to deal with. And then as part of this, we'll talk about not just the space system, but also the flight system, but also the overall system. It includes the ground system, the science teams, all of those things, and how you develop a team and develop an architecture for the mission that allows us to do the things we need to do for as long as we need to do them. So just quickly, for those who haven't seen it before, this is what our trade spaces look like. We came into the study with some very broad engineering goals. Readiness, NASA has asked us to develop a concept that could be launched by 2030. So essentially 9 years from now, almost. That's a pretty good challenge. And you'll note my sentence down at the bottom in yellow. It says the study trade includes only existing or near existing technology, because the reality is we don't have much time to be doing technology development for a mission like this. After significant technology development in heat shield technology, Parker Solar Probe still took 11 years to go from a pre-phase A all the way in study, kind of like this one really, all the way to launch. And so doing something like this in 9 years is very ambitious whenever you start thinking about things like, for instance, solar sails, which may be a very good technology and may someday really be beneficial, but for a launch in 2030 is very impractical. We also have science operation at range, and so we want to be able to perform useful scientific measurement and return data to Earth from 1,000 AU. We want power to be no more than 600 watts available at the beginning of mission and no more than 300 available at the end of mission. So we're assuming degradation of the RTGs, and I'll show you some details on that later. And we're planning to be able to operate a mission within that budget for that worst case power budget. And again, the longevity here, the lifetime here is not less than 50 years. And so these are, as Ralph has said, independent criteria, but they're the initial inputs that we were given for the study. From this, we also, as we started the detailed study, we knew we had really 3 options for trajectory. They've already been touched on a little bit. There's what I call a passive Jupiter gravity assist or propulsive Jupiter gravity assist, and then the solar Oberth maneuver. And then we have, again, multiple payload options. We're not trying to define a payload here, but we need something to plan against and to understand what the flight constraints are. And so we are looking at mainly a helio mission with the instruments that Pontus will tell you about. Again, these are not selected instruments. These are candidates that we're using to provide inputs to the study. But then we're also looking at potential planetary or astrophysics augmentations, and you're going to hear a whole lot more about this week. And we're also looking at payloads that could vary over a range in terms of mass or power, right? So you can build the payload that we've got right now that we're using as a baseline. There are things you could add to that. There are things you could take away from that. Those are science trades, but they have impact, right? So adding instruments it will affect how we can accommodate instruments. It will affect the mass of the system. It will affect the cost of the system. And so we're trying to get down to what we think is a reasonable analog for what we would fly in a mission like this. So what is our study plan? We really are developing this in 3 phases. There is the first phase really has sort of been completed, and that's to identify the trade space. That's where we've been working with the science team to develop these example payloads. We had surveyed previous studies and similar mission concepts to identify the technology base that we're going to consider here, and also identify the realistic mission trajectories that we talked about. We're sort of at the end of phase 2 right now, where we've developed that baseline concept. We've looked at some of the augmentations that are needed, and we'll go into details about all of these things throughout this presentation. And then phase 3, which we're going to complete next year, is to take a look at this solar Oberth maneuver concept. And because it is such a different mission, while there are things that will overlap, for instance, the avionics system for the missions that we're considering right now versus the solar Oberth case, they're going to be very similar, but there are going to be so many more differences in the physical layout and the things that we're required to do for that mission. It really is a separate case entirely. And so while we're not going to start from a fresh sheet of paper, it'll be a pretty clean sheet of paper whenever we start that. And so where are we today? I've already told you about the trajectories, so we won't dwell on that. I'm going to show you more of those. And then Wayne Schley will definitely give you more than you ever wanted to know about these trajectories whenever we talk about them. I think it's on Wednesday. We have a mission timeline and a science data downlink strategy. I'm going to touch on that today. And Dave Copeland and Reza Ashtari are going to talk about that in more detail again later in the week from a communications perspective. And I know Pontus and the science teams will be talking about that a lot and how to use the available downlink. We have identified an example payload. They've actually put together an example science traceability matrix from this, and we've derived a set of mission requirements using that to be able to, again, develop the concept that we're looking at to see what the feasibility here is, to understand what the constraints are, all those kinds of good things. And then we've also looked at that as well or beginning to look at that for the augmentation side of things. I'll give you an example of something that's come out of that, for instance, in the Helio payload that we're considering. One of the things that's included are 50-meter wire antenna for plasma wave studies, right? When you start looking at that, that pretty much says you're going to have a spinning spacecraft. It pretty much defines what the spin rates are going to be and how you deploy those things. It defines the delta V requirements because you're now dominating the moments of inertia of the spinning spacecraft with those booms. And so being able to have this example payload lets us poke into these issues that are going to come up with this whenever it's time for a real mission to be developed. And again, our baseline mission concept again is to, one of the main things that we're trying to accomplish here is to maintain flexibility and understand the constraints like the one I just talked to you about. So before we go on anymore, I want to make sure that we get our architecture nomenclature correct. You're going to hear a lot about option 1, option 2, and option 3. This defines what those options are from the engineering team's point of view. So the first is the ballistic Jupiter gravity assist, where we simply launch on a 4-stage vehicle to Jupiter. We use a ballistic flyby to give us some delta V, and from that we target our path out to the interstellar space, interstellar medium. There are variants to that. Right now we're mainly focusing on variant A, which is the heliophysics payload, the one that I'll show you, the one that Pontus will start with. There's a variant B that will be looked at here with a planetary add-on. So this would be the case, for instance, where we might target the possibility of doing a Kuiper belt object flyby as part of the trajectory out, and then we would adjust the example payload to include instruments that would be able to make those measurements, to be able to take those pictures and so forth. Option 2 is our power Jupiter gravity assist. In this case, we use a 3-stage launch and carry a solid rocket motor with us to Jupiter. At Perijove, we would then fire the solid rocket motor to give us even more delta V. Right now, we've only looked at the variant A, which is the heliophysics with a medium payload. As part of this, we will continue to look at the variant B with this one as well. It turns out that when you look at it at the spacecraft itself, there's not that much difference between the spacecraft with regard to option 1 and option 2. The biggest change is the amount of propellant you have to carry, because you have a bigger delta V burden whenever we're carrying a 3,000 kilogram solid rocket motor with us to Jupiter. Option 3 is going to be the solar Oberth maneuver case. This is a case that I've got in more detail later. I'm not going to cover that one right now because I want to focus on the concept for options 1 and 2 first. Okay, so what example payload are we working with? This is what we got. I actually stole this slide from Pontus, so thank you, Pontus. This is the sort of 90 kilogram kind of case that we've been looking at. It includes instruments that you might expect for a mission like this. If you look at these instruments in a little more detail, you'll see that some of them want to be ram facing. Some of them want to look at all space. Almost all of them need to be boom mounted in some way, shape, or form. So if nothing else, we can get instruments out past the edges of this big 5-meter high gain antenna that we're having to carry. So there are considerable challenges associated with accommodating the fields of view for these instruments. And there are quite a bit of conflicts here that we have to sort through. And that's okay. That's part of what the engineering team is there for. But I just wanted to folks understand that the more instruments we put in this payload, the harder that job is. And so there is a penalty as we add things to the payload. That's not just cost, it's not just mass and power, but it's also the difficulty of just even getting them to be able to work together. Let's see, our augmentations are primarily cameras and other kinds of instruments like that to be used in detailed imaging. We think we understand what those requirements would be for fields of view and so forth. For sure, well, I'm not going to say for sure, because you may hear later about the case which is something we're sort of calling a hybrid right now, where we have a camera on a spinning spacecraft. But in general, the way we've been thinking about it is if we're going to do the planetary augmentation, that may require 3-axis control. There's also some issues of a high data volume flyby that we would have to work out in terms of the concept of operations. Those things are things that we can definitely work out. Okay, so let's go into some results. I want to show you first sky map. This is for option 1 Jupiter gravity assist. And let me just walk you through this just a little bit so we can so you can see what's going on here. So if you look across the bottom in little tiny letters, you might be able to see dates. So here is 2030. If you can see my cursor down on the right-hand side of the chart, which then loops back over onto the left and works back again to the 2040, 2041 kind of time frame. You'll notice a color scale on the right-hand side, which is speed at 1,000 AU, and this is at in AU per year. And so what you can see is that there are particular directions we can go, which are very favorable for a given launch year, and other directions which are not favorable to be able to get the speeds that we're looking for. We've also got on here the nose of the heliosphere, which is here. And then also something that's very hard to see on this chart, but is really there, I promise. There are contour lines that show us where the ibex ribbon is and so forth. And so what we can use this for then is to start thinking about where might we want to send a spacecraft like this. And one of the long science discussions that's being had still is what should we assume for a candidate trajectory. And you'll see over here on the side some discussion about that. We have, in fact, come to an agreement with the science team to pick a candidate, and it is over sort of in this region right here. That does not mean we would launch in 2040. It just means that this is an example trajectory that we would use to understand concept of operations, flight times, constraints on the system, and things like that. If we to go to option 2, and Wayne will give you much more detail later, because of the dynamics of the system, these high-speed areas will move around a little bit. And so we picked another target which is very close to this original target that would be used in the case of the powered gravity assist. All right, moving on to the next. Part of what we were able to do here is to also look at the dependence of this on mass. So heavier spacecraft means we'll go slower. For a given spacecraft mass, we can pick out a speed, and then we can vary these trajectories across those spacecraft masses, which has been done here. And you can see that we can generally get something for option 1 that's in the range of about 7.6 AU per year down to something like 7.25 AU per year. And an interesting thing about this is that there's a fairly linear relationship here between the a mass change in the spacecraft and speed change, and it's about 0.17 AU per year for 50 kilograms. We did the same trade for option 2, and while the speeds here are generally higher whenever you go to an optimized target for option 2, the slope of this line is almost exactly the same for the 2 cases, for option 1 and option 2. This gives us a lot of flexibility then with the system. There is no hard and fast mass that we have to achieve for the spacecraft here. We have the ability to make trades on reasonably small amounts of mass with speed and be able to compare that to impacts on the science, for instance. Okay, so operation scenarios, and I'm just trying to keep an eye on the time here for folks. There are really kind of two operational scenarios that we're looking at in general. The first is the baseline scenario. That's the one we're mostly discussing now, that you see across here. This is a spin stabilized system, 50-meter plasma wave wire antennas again. And so that's kind of the baseline of what we're going into with ConOps here. You can roughly divide the mission up into 3 phases, sort of an inner heliosphere phase, an outer heliosphere phase, and an interstellar phase. The reality is from a spacecraft perspective, the mission doesn't change from phase to phase so much as this allows us to target specific science goals and science observations that want to be made in these different regions. And so, for instance, whenever we show a plot of the data volume per week that we have made available to the scientists, this will affect how they would divide that up into the various instruments and the various experiments that they're doing. And this kind of gives you also an idea of the distance ranges that we're considering for these various phases. If we go to the planetary or astrophysics augmentations, now maybe we're a three-axis stabilized spacecraft at least some of the time. We have to do something about the plasma wave antennas, and so maybe we're looking at more rigid antennas that are shorter. And so when you do that, you can see the regions of interest for the various planetary augmentation and astrophysics augmentation. All right, so given that we have some trajectories now, let's move to launch vehicle and figure out whether we can actually launch into those trajectories. So what I'm showing you here is what we call a C3 versus mass plot. C3 is a characteristic energy that's given, it's basically a measure of the performance of the launch vehicle stack. We've worked with the folks out at Marshall, as Ralph has mentioned, to do a very extensive trade on, in this case, we're showing you the SLS configurations, but we've also looked at pretty much every other vehicle that's on the table right now that's a realistic launch vehicle case. And as you can see, the SLS Block 2 is the one we're concentrating on because that's really the only option here. There are other options for third stage. So for instance, we've looked at just a Star 48, we've looked at a Centaur with a Star 48, casters, and so forth, and tried to define just how much mass could be lifted for a given C3. The boxes that I show you here, numbers 1, 2, and 3, are for our different options. So for option 1, we need to launch somewhere in this range. And in fact, that's what Wayne is using as his input to his trajectory analysis, a C3 of just over 300. That's very high, by the way. Here's New Horizons down here at 160, 158 or so. Parker Solar Probe was just slightly lower than that. So we are talking about a very high performance vehicle if you want to do this. And then that gets us in the, somewhere around a metric ton kind of range into that orbit. Option 2 is a lower C3 because we're carrying the solid rocket motor stage with us. And so that's not included in the stack analysis. And so, but we also have to account for that mass whenever we're talking about lifting this vehicle up to Jupiter for a gravity assist. And so that's shown here. It's still achievable using some of these configurations. And then for the solar Oberth maneuver case, we show that on here as well. Again, this gives us a mass range for what we need to target. It is not clear to me at this point in time that we can build a system that can live within that launch vehicle capability. Okay, just basics on the spacecraft. Let me just run that down real quick. And because everybody likes the pictures, first thing I did is put a picture of what the spacecraft might look like over here on the right-hand side. And I'll give you some more details on this in a bit, but just for scale, this is a 5-meter diameter high-gain antenna. Generally, we're looking at masses for the spacecraft as a whole, including the payload and propellant and any contingency we need to carry, in the 850 to 950 kilogram range. So we're looking at something just slightly less than a metric ton. There will need to be 2 RTGs on the system. We're assuming characteristics that are given to us for the next generation RTGs. We'll discuss that at the end of the week whenever June comes on board to tell us about RTGs. This is essentially the same input that was given to folks who were doing the planetary decadal survey studies. We assumed that would be a reasonable starting point for understanding what the RTG capabilities and constraints were. This considers a payload in that 90 kilogram range, as I told you. Heavier payloads are possible, right? I could certainly increase this launch capability from 870 up to some higher number at the cost of some speed. But as I say here, there are costs associated with instruments. There are risks associated with instruments and engineering penalties that we have to deal with associated with adding instruments. And so trying to get this to a, what I would say is sufficient to cover the science you want to do without adding too much extra burden is going to be an important factor. And I've mentioned the different types of payloads that we have before. Telecom, right now we are looking at an X-band system to achieve something like 500 bits per second. That's a goal at 1000 AU. And to do this right now, it's a very large fixed dish. And it's very unlikely that we can make this any smaller without doing something like going to a Ka band or going to some sort of optical system, which are on our trades list that you'll hear about later. For control, again, I've mentioned this is going to be either a spinner or some sort of 3-axis hybrid, depending on the payload. It will be thruster-only control. We know that wheels don't last for 50 years, and so we're assuming from the beginning that we can't use them. Very similar to the approach that was taken on New Horizons. And also, just to lay it out there, telecom is going to drive the pointing and control requirements. Whenever you're trying to point this dish back to the Earth at 500 AU or 1000 AU, the control suddenly becomes very, very difficult. All right, some more information about the spacecraft accommodation. Again, this is a physical layout that's used to study the mission and spacecraft constraints and capabilities. So at the end of the day, spacecraft could look completely different. I don't think it'd be that different, but it very well could be. It is mainly an octagonal spacecraft body, which you can sort of see here at the bottom, with an interior center cylinder and prop tank, so nothing too out of the ordinary there. We have two RTGs in opposition for balance. We would use the waste heat from the RTGs for thermal control, much as New Horizons and other missions have done. There are ram-facing instruments. This is actually the ram-facing side in this mission because we're assuming we're going away from the Earth. And so there are instruments you can see on that bottom deck that are ram-facing. This is also the ring that we would use to attach to the launch vehicle and the solid rocket motor. So that's all got to be balanced very well with things like field of view concerns and so forth. And you can see there are a number of booms here. There are 2 booms for magnetometers. Again, we're using 2 booms for balance. And so that's the subject of a little bit of a trade that's going on right now as well. You can see the 4 wire antennas here. These actually are chopped off in this picture. They extend way, way, way past this. Remember, these are each 50 meters long. And also, let's see, there you can sort of see, for instance, down here in the bottom left-hand side of the spacecraft, there are instruments that are extended out past the dish to make sure that they have clear fields of view beyond that 5-meter dish. From a spacecraft architecture kind of point of view, really what we're not looking at something that's too different from what we're already flying. If you look at this block diagram, it's got all the usual pieces. The flight environment is in what I call in family with other deep space missions. There's nothing super difficult about going out to the interstellar medium from a, spacecraft has to do something special kind of standpoint. We'll pick up some radiation dose in the Jupiter Gravity Assist, but we think that is somewhere in the 100 kilorad range, and so is achievable in the kinds of parts that we can buy off the shelf now. We also have mass to accommodate things like shielding and things like that if we need to use it. We're looking at redundancy. This is the block diagram you see here is a highly redundant system, and all the pieces can talk to all the other pieces, and so there's a lot of ability then to be able to handle faults and so forth. Also, one of the things that we decided early on was that even though most spacecraft these days have multiple sorts of interfaces for instruments, we're going to simplify things in this architecture by just assuming up front that everything that can be will be connected to the avionics through SpaceWire. At the end of the day, whenever a real mission gets flown, maybe it's not SpaceWire, it could be something else. That team can make a different decision about allowing other sorts of interfaces into the avionics. That's okay. But just for simplicity's sake right now, and the purposes of being able to do reliability analyses and build the tools that are needed for that, we made this choice for the architecture right now. And again, it's an X-band system using TWTAs and multiple antennas because we don't want to use the high gain antenna necessarily when we're early in the mission. Just a little more detail about the avionics system. That's this middle piece right in here that we'll talk about. It's really going to consist of just single board computers, solid state recorders. There's a card there for analog interface to things like thrusters, thruster control and things like that. Everything else is on this space wire. We did also assume that we can use galvanic isolation on the space wire, which is a technology that exists. And what that means is we would have the ability to, so if a failure occurs in an instrument or a component, it would not take down the entire space wire bus, one side of the space wire bus. It allows us to isolate failing pieces and allows for graceful degradation from a reliability perspective. Specific choices for processors and other components, we don't need to do that right now. As part of the next phase of a mission, should it go forward, would be things like defining what does this single board computer look like, what is the details of the processor that we would use, what sort of FPGAs we would use, things like that. We need to understand enough about the parts that we need to use to be able to do things like examine their lifetime and reliability requirements. But beyond that, there's no need for anybody to make specific choices. So we haven't done that. And then again, as I said, we're assuming that we can get parts that are sufficiently radiation tolerant during a Jupiter gravity assist, and that looks like a reasonable assumption. For power, I show you over here on the top right-hand side the assumed RTG characteristics. This is for one unit. Let me just be clear about that. So a single unit would be 300 watts electric at beginning of life, would weigh something like 60 kilograms. At end of life would give you about 150. And then when we combine two of these together, would give us the 300 watts end of life that we need to have. Typical voltages for a spacecraft, again, this is a choice that could be made differently in the next phase of a mission. But for right now, this is the assumption that we're assuming for the system study. And then we of course are requiring a launch availability of 2030. That's consistent with the plans that June will tell you about later in the week. Our worst case power mode is whenever we're very far away from the Earth and we're 50 years into the mission and the RTGs have degraded into 300, down to 300 watts, but we still want to run the payload at the same time that we're being able to communicate with the Earth. And so when you do that, the numbers work out like this. We still have some margin against that 300 watts. So we think that we are in reasonably good shape for worst case power. And one thing you might notice if you look in detail at the block diagram is that there's a battery on there. We don't really expect at this point that we'll be able to find a battery that's going to be practical for a 50-year lifetime, but we included such a thing in the block diagram just in case, because it would be very helpful late in the mission for smoothing out peak loads, for instance, right? So where you are able to do something higher, you use higher power for a short amount of time and then recharge batteries. Guidance and control. So the guidance and control subsystem, as I said, it's going to be driven by the pointing control, right? For increasing our downlink data rates. We did choose our operating frequency to be able to best explain our pointing capability and available aperture. That is an X-band system. And then when we use this dish at X-band with the power that we're talking about, it looks like something like our 0.2 degree requirement on pointing control. That assumes that we have stable spinning about the high gain antenna bore site. That itself offers some interesting challenges there, and Gabe Rogers will tell you later in the week about some cases where things like bore sites have shifted and cause problems with communication. So we're working through all the details of that. I would also note for guidance control, another big impact is this long, complicated process for deploying wire antennas. We've done it before. APL in particular has done it on Van Allen probes. And so we have some experience with this. And so we can give you some very good information about what it really takes to do that. And look forward to that this week with Gabe's talk as well. As far as GNC components go, we're talking about star trackers, we're talking about IMUs, and we're talking about sun sensors with thruster only control. So again, nothing exotic here, nothing that's going to be a big issue. Star trackers that will work on a spinning spacecraft are a little more difficult to come by now. So there may be some engineering development associated with rebuilding the capability to have a star tracker that works in a spinning spacecraft, but that's something we think is achievable, just need to work out the details. Telecommunications, I'm showing you the telecommunications block diagram here. Again, you can see multiple antennas, highly switchable system. It is based on a TWTA amplifier, and I think we've allocated 90 watts for that TWTA, although I will say we are looking at this from a redundancy and fault tolerance aspect, especially if we were to have a single RTG failure. At end of mission, we want to still be able to accomplish at least something like a mission. And so, again, the subsystem really consists of the usual things, right? A radio, a TWTA, low noise amplifier for receiving, a low gain, medium gain, and high gain antennas, and the usual kinds of configurations, and then all the waveguides and switches needed to hook everything up redundantly. And again, as I said, Dave Copeland and Reza Ashtari will show you later on that we do have some ongoing trades for ways we might be able to reduce the mass of that antenna by going to some more advanced architectures that currently exist. And also there's this issue of whether we should go to Ka-band, which would require much tighter pointing requirements, and so perhaps a more complex antenna, and also optical, which again has some implications on pointing and also for ground stations. You've seen this slide before. I just threw it in here as a reminder. We're going to start talking now a little bit about concept of operations and how we would actually operate the system, especially from a data downlink kind of issue. So again, just as a reminder. So I'll show you over here on the right-hand side, and again, I'm not going to go into detail with this, but we did do a study of, we did do a study of the possible ground stations we might be able to use with this system. And you'll see that there are some very interesting ones there, like the arrayed DSN. That's a capability that exists. But we also are noting here that deep into the mission, we would be required to use something like the next generation VLA to communicate. That's just sort of the fact of life. And so that's something that we're showing to NASA from the very beginning. And they're aware of the need for something like that. And so it's being factored into the decision-making process. And then again, we also show you here on the left-hand side what our data downlink assumptions are for the various phases of the mission. So first portion of the mission out to Jupiter is what we call our early operations and commissioning. We would operate on the LGA and MGA antennas. Pretty straightforward to talk to the DSN on a single 34-meter dish. And we would use the typical contact plan of something like 3 contacts per week. We may need other additional contacts for early operations, navigation types of things. For the inner heliosphere, which is out to 70 AU, that's something like 10 years into the mission. We would operate off the high gain antenna, and even going forward from that. So we would never use the medium gain antenna or low gain antenna again. At that point, for a while, we can use the DSN on a single dish, and then we need to start arraying those. And so we would go to 2 dishes and then 4 dishes. And we would do that something like 3 times per week again. Once we get to the outer heliosphere, though, we've got to switch over to the next generation VLA. And that's out to from 10 years out to about 35 years out. Again, we'd look at something like 1 contact every couple of weeks. And here a contact is probably on order of 10 hours or something like that. As we get further out, because of the difficulty in communicating, and because we want to make sure we can get meaningful data back down, we would move that to about one contact per week. And if we do that, our data downlink concept of operations looks like this. Something on the order of, so if this is data volume basically in a given week as a function of mission time through here. And you can see here is where our 50-year mark is. And so you can see the boundaries here with the different phases of the mission as well. And the nice thing about this is that we can then hand this to the scientists, and they can after they've subtracted off what we've told them for housekeeping, spacecraft housekeeping and health and safety, and then margins, then they can go off and they can plan how to fill these buckets in any given week of the mission. And I would note that significant data return is possible even through an extended mission phase. And so, as I mentioned before, we are still thinking about how this changes if we have an RTG failure and whether we can complete the mission. And so that might tweak the architecture just a little bit. Okay, moving on to reliability. Obviously, we want a long duration mission, and so that's going to immediately raise some questions like, can we even do that? So let's address that by going back to the historical record and see what it tells us about long duration missions. Let's identify the major technical challenges in building a long-lasting spacecraft. Let's identify a framework for providing confidence to decision makers in the science community that we actually can do this. And that's ongoing work that's going to be talked about this week as well. Clay Smith will be addressing this in great detail, I think on Thursday it is. And so we've developed a concept. We can then use that concept to develop reliability models at a system level that lets us do things like identify the risk drivers and mitigations, which we're already in the process of doing. We can try to quantify uncertainties associated with these models. And then we can then feed that back into the science team so that we can look at the science objectives from a reliability sense and make sure that the system itself is not depending on a single measurement or a single instrument to be successful, right? We have flexibility and we have robustness in how we're performing the science. And then as a part of that, one of the things that we have to do is we've got to work on ways that we can understand what the reliability of electronics will be for a 50-year mission. And a lot of that goes back to physics of failure reliability modeling, and we have experience with that. And we've got some good partners that that Clay will tell you about as we're looking forward into that. From the ground system side, we have to remember that a mission isn't just a spacecraft. A mission starts with a spacecraft, but also includes things like ground stations for communication, mission operations centers, navigation teams, mission design, a science community that will both give us plans and then also take data and turn those into papers, right? And so the question is, how do we organize for a 50-year mission for success? And again, I think Glenn Fountain is going to be talking later on this week about some of the thinking that we have in this regard. But really, it really comes down to two principal goals, right? Identify the processes to make sure that all of these elements are going to work together to ensure a successful outcome. And then provide information about current and past missions that show that we can actually do this, that we can build teams that can be adaptable over a 50-year lifetime, and that can provide for the knowledge transfer and for the knowledge just storing even that we need to do to be able to do this. So let me then wrap up the discussions of the baseline concept that we've been talking about and move over to the solar Oberth maneuver. And again, this is going to be the focus of our next phase, starting probably in February or March or sometime like that. So pay attention to next year's workshop for more. But essentially, the mission description looks like this. We would launch, we would go to Jupiter, we would then go to the sun, and we would fire that solid rocket motor that we're carrying at perihelion. The perihelion may be something like 3 solar radii. Issues that are part of this is that we've got to control that trajectory, so that we've got to make sure that we hit the perihelion that we want, that we get to Jupiter and hit the Jupiter point that we want. We have to protect the system during the approach, perihelion, and departure prior to spacecraft separation. And so I'm showing you a picture of, this is again a very early picture using a New Horizons spacecraft, not the concept that we would put forward, but just to give you an impression of what this might look like, right? You can see the spacecraft attached to a solid rocket motor. Here in this picture, the sun is at the top of the screen, and so you see something like a partial hemispherical kind of heat shield that then would protect everything from the sun. So let's look at some of the challenges associated with a concept like this. First of all, if you've got any asymmetry in this heat shield, you're going to be producing some very large torques from solar pressure. And we've looked at those in detail, and they are very large. Solar Probe is dealing with this, but they're dealing with it from 9, and well, we haven't even gotten there yet, but we will be dealing with it from 9.8 solar radii, not from 3. And if it goes like 1/r², you can already see that this is orders of magnitude bigger than we might have dealt with the previous missions. The other thing that we've got to deal with is that as this solid rocket motor fires, you're losing a lot of mass out of the solid rocket motor. That's the whole point. And so the center of mass is going to shift on us. And if it shifts, that's also going to cause really big torques on the system that have to be controlled, right? And so what that's driving us to is having not only a solid rocket motor, but also a large propulsion system that can be used to control this this thing is thrusting very, very highly. And so we've got to be able to control that. And so that is going to be a big mass driver. Another option is to have a smaller propulsion system, but a very large ballast mass that balances the heat shield and balances it in such a way that we can retain control over the shift in center of mass of the solid rocket motor. Again, that's going to be a very large mass. And so hence my comment from before that it's not even clear to me that we can build a system that would fit within the capability of the SLS plus the other stages. In addition, the heat shield's got to survive higher temperatures. I'll show you some more information on that, but it means that either it's going to be an extremely heavy shield, or we got to develop some new technology that can make it a little lighter. And so I've got some words on that on my next slide. And let's see what else. Yeah, so the other thing when you look at this picture is you immediately see that you filled up a very large portion of the sky with this heat shield. And if we have a ballast mass on the other side, that's going to make it even more interesting. And so all of a sudden we got to figure out ways of, where can we put GNC sensors? Where can we put the control thrusters? What happens when you fire a solid rocket motor with a shield hanging over the edge of the nozzle? All of these things are issues that we got to look at. And so as you can see, this is going to be a very complex problem. So just quickly on this, I just wanted to show you a little bit about the temperature differences that we're talking about here. So if you look at the little chart on the right-hand side of my slide, you can see some information about Parker Solar Probe. So Parker design range is up to about 1700 or so Kelvin. We do see, what our limits are here for carbon-carbon. It's, up well above 2500 Kelvin. So that we know the Parker Solar Probe is going to be okay. We're going to be able to work. The problem here is that whenever you start looking at heat shields at 3 solar radii, for instance, you're already starting to talk about temperatures between 3000 and 3500 Kelvin. And that's way beyond the limits of what we can do with something like a Parker heat shield, all right? So one of the things that we've been doing is we've been working some basic material experiments that allow us to look at the possibility for reducing the mass of a heat shield that would be required to be able to survive these kinds of temperatures. That low mass heat shield design has to be developed. It has not been developed. We only have some very preliminary small material studies, and you'll hear about those this week, that lets us get started. It's not clear that it's even possible to build something like this. And so a large amount of development work would have to go into something like this, and that may also take us beyond the 2030 launch opportunity that NASA has asked for. Okay, so I think this is my last slide, and then we'll take some questions. Next steps. Well, we have a baseline concept, so that's great. There are some optimizations that we're still working on. We're pretty sure this mission could be accomplished, though. We do have to worry about the reliability of electronics and materials, and that is probably the biggest open question for the baseline concept. And those are being dealt with. You'll hear about some of that work as we go along. And the next case study that we're going to work is the augmented mission, and this is probably going to come up in the late 2020, early 2021 timeframe, where we need to rework that instrument suite physical accommodation based on, for one thing, the input that we get out of this workshop as the scientists tell us what the example payload should be for that case. One of the things that we'll have to do if we want to do this is to replace the wire plasma antennas with something that's more rigid that can be controlled in a 3-axis mode. And so that's a discussion I think that's going to be coming up this week. There are going to be changes to the delta V requirements associated with going to this case. That's okay. We can work through those pretty easily. And again, we'll update the concept based on that. And then probably some reworking of the concept of operations, because we're now doing a planetary flyby, which is sort of different from the heliospheric kinds of measurements that we've been doing. And hopefully we'll wrap that up in the early 2021 timeframe. Just about the time we want to start working on the solar Oberth maneuver case. As I said here, it's probably going to be a full reworking of the concept, and not clear that it's feasible, but we're going to do the work to show that, or to show that we have a case to be made. And then finally, there's going to be a final report where we document all of these case studies. And let me also just add, we're also publishing papers on this as we go. So if you pay attention to the IEEE Aerospace Conference, for instance, we've got some four or five papers in the conference this year talking about these various topics, a lot of which you'll see here. And we're going to continue to publish like that as we go along. So with that, I believe that's my last slide. I'm going to get out of slideshow and stop sharing, and maybe we can have some time for some questions.
Thank you, Jim. We do have time for questions. If anybody would like to ask Jim about the spacecraft design or the trajectories that we've covered so far, the mission architecture itself, accommodation of the payload, where we're putting instruments, all of these things are on the table. And I guess, Jim, I have one question for you. The way that you talked about the spacecraft design not being fixed so far, that the spacecraft could change its configuration from the images that we have now to something else, but that wasn't necessarily going to happen. Could you talk a little bit about that? Why do we have even a 50% level of confidence that the general configuration
Sure.
looks like it's something that we A, could build, and B, would suit?
Sure. So assuming we continue to fly the 5-meter dish, that's going to be the big driver for laying out the spacecraft. It's got to go on the side that it's on the spacecraft. The fact that we have all of these different things that have to be balanced so the spacecraft could spin pretty much drives you to something like an octagonal shape. There really aren't a whole lot of choices there. There could be differences in how a design team chooses to get instruments out beyond the dish. So for instance, we're showing some arms that stick out that get instrument fields of view clear. There are other design possibilities that could go into that. Those are in the details though. It's not going to change the mass very much. It's not going to change the overall aspect of the spacecraft very much. Really, the things that fix all of those things are the fact that we've got the big dish, or even some kind of big dish if we go to Ka band, for instance, and the fact that we have instruments that want to be on the RAM side, some instruments that want to be clear fields of view for full sky, and then some that want to be way out on booms like the magnetometers. So once you put that in, there's really not that many choices that can be made in terms of big overall architecture.
So it sounds like the design, the physical layout of things so far is driven by the launch load requirements and the big pieces that you have to accommodate first, like the dish. Yep. And the RTGs themselves are fairly heavy. And once you've accommodated that, you kind of attach, if you will, everything.
That's exactly it.
To that core structure that that you must have in order to support at least that large dish.
Yep, that's exactly it.
All righty. Now, everybody remember that that later on in the week we're going to have some detailed discussions about communications and data plans, discussion about the solar Oberth maneuver and the thermal material research that we've done over the last year in other areas. But we're not going to dive too far into some of the other engineering areas. And so this is a good chance to pick at those, if you will, structures and other aspects that may be of interest to you. For example, earlier there was a question about the thermal stability of the spacecraft, and by earlier I mean during the student session this morning, while we were using the Miro board to generate discussion. Somebody asked about the thermal cycling of the spacecraft. Is that going to be a problem? And for some satellites, Earth-bound satellites, thermal cycling is definitely a big deal.
Yep. Because
you're going in and out of the shadow of the Earth. But this spacecraft, once we've launched, will pretty much hit a thermal steady state and probably not deviate from that baseline temperature profile much at all for ever.
Yeah. You'll probably see some thermal impacts due to albedo at Jupiter, things like that. But beyond those cases, it's going to be a very stable system from a thermal perspective. And that's typical for instance, New Horizons the same way, right? It's got fairly constant thermal input from the RTGs, minus the natural radioactive decay, and there are no cycles in the sense of eclipse versus solar exposure and things like that. Same thing here. It's going to be very similar.
And while at a spacecraft detailed design level, understanding what those temperatures are is critical. The fact that we know from New Horizons that it's pretty straightforward and stable relieves the team right now of having to go through risk mitigation on that front at this point in time.
Yep, exactly.
pretty benign from a design perspective. All right. So we don't have any questions from the attendees at this point, but we do have a couple more minutes. I do want to hold true to our promise to make sure people get breaks. We have our next session is at, let me just double check the calendar schedule, make sure we're right on target here. Is at 1 o'clock. It'll be science with Pontus and with Elena. But I do want to make sure that we give folks a chance to chime in here. I think very good. Excellent. Let's thank Jim. And actually, we didn't do this for Ralph, but I want to do this. Could people please, since we have we're using the Zoom tool here, you can use the chat or you can use the Q&A. Gabe Rogers is saying that, says, I guess you did too good a job, Jim, covering all the bases. If you want to just put in a chat real quick, anybody, and everybody, just say hello. Thank you, Jim, and we can go ahead and take a break. I think I can do that, can't I? I am going to do that. Let's see. Thank you, Jim. I can't type right now. There we go. Very good.
Right.
Very good. Thank you, Jim. Excellent.
Thank you.
More to come on the engineering side. A lot more details on the challenging areas that Jim and the team are taking on. So please stay tuned for that over the next couple of days. And it's 12:41 Eastern time right now. We'll reconvene at 1 o'clock. At 1 o'clock for the science discussion. Thanks all very much, and we'll see you again real soon.